You have seen the M1 Abrams in footage. That unmistakable silhouette, low profile, wide tracks. The long, smooth-bore barrel extends from a turret that moves with a precision that seems impossible for something that weighs 68 tons. The most capable main battle tank ever fielded by the United States Army. A machine that has dominated every armored engagement it has entered since it first rolled into combat in 1991. And somewhere in the background of that footage, if you listen carefully, you can hear something that does not sound like a diesel engine. It does not sound like the deep mechanical rumble of a truck, a bulldozer, or any other piece of heavy equipment you have ever heard. And it sounds like a turbine, like a jet engine, like something that belongs in an aircraft, not in a ground vehicle. That sound is not your imagination. The M1 Abrams is powered by a Honeywell AGT 1500 gas turbine engine. Not a diesel, not a gasoline engine. A gas turbine, the same fundamental technology that powers military and commercial aircraft, is installed in a ground vehicle that operates in deserts, jungles, and urban environments where jet fuel logistics are a constant, expensive, and operationally significant challenge. And the story of how that decision was made, who made it, why they made it, what it cost, and what it continues to cost is one of the most consequential and least discussed procurement decisions in the history of the United States Army. So why does the most powerful tank in the world run on jet fuel instead of diesel? What does a gas turbine engine offer that a diesel engine cannot? Why did the Army choose a technology that consumes dramatically more fuel than the diesel alternative? And what does that consumption rate mean for the logistics of keeping an armored force in the field? Why did the original competition between General Motors and Chrysler produce a result that the Army's own testing recommended against? And who overrode that recommendation? Why does the M1 Abrams consume fuel even when it is sitting completely still? And why, after more than 40 years of operational experience with the AGT 1500, has the Army never replaced it with the diesel engine that its own engineers originally preferred? Here's the one that should reframe everything. According to the knowledge base, the M1 Abrams gets roughly 0.5 to 2 miles per gallon, depending on terrain and operating conditions. A typical M1 tank battalion requires significantly more fuel tankers and support vehicles to keep up with the high fuel demand, including added 5-ton trucks and 5,000-gallon trailers. The turbine engine consumes 83% more fuel than diesel-powered counterparts. In a sustained armored operation, the fuel logistics tail required to keep M1 Abrams tanks moving is not a minor inconvenience. It is a strategic constraint that shapes how the Army plans and executes armored warfare. And it all traces back to a decision made in July 1976 that went against the Army's own recommendation. Most people who know the M1 Abrams runs on a gas turbine assume the decision was made for performance reasons. The turbine produces more power, the tank goes faster, the acceleration is better. The Army chose the turbine because it made the tank more capable on the battlefield, and the fuel consumption was an acceptable trade-off for that capability. That assumption is partially correct, but misses the most important part of the story entirely. The turbine does produce significant performance advantages. The AGT 1500 generates 1,500 horsepower, a power output that gives the 68-ton Abrams a power-to-weight ratio comparable to many sports cars and enables the rapid acceleration and high cross-country speed that define the tank's tactical character. Those performance advantages are real and operationally significant. But the decision to use the turbine was not made primarily by the Army's engineers based on performance testing. It was made by civilian defense officials over the objection of Army leadership in a procurement competition that the Army's own evaluation had already decided in favor of a diesel-powered design. Understanding why requires going back to 1976, and a competition that was decided by factors that had nothing to do with what happened at Aberdeen Proving Ground. Here's what actually happened, and why the M1 Abrams burns jet fuel today. When the Army launched the M1 tank program in the early 1970s, it was determined to avoid the cost overruns and failures that had plagued earlier efforts like the MBT-70 and XM803. As the Slashgear website documents, the Army set a strict cost cap, limited requirements, and demanded working prototypes instead of paper designs. General Motors and Chrysler went head-to-head. General Motors proposed a new variable compression diesel engine. Chrysler pushed for a gas turbine. Tests at Aberdeen Proving Ground showed General Motors' diesel-powered tank performed better overall, offering superior armor protection and more reliable fire control. The Army had made its choice and was ready to award the contract to General Motors. In July 1976, Defense Secretary Donald Rumsfeld halted the decision. Against Army recommendations, he ordered a redesign to accommodate the turbine. Deputy Defense Secretary William Clements and other Pentagon officials pushed the shift, arguing the turbine represented the future of armored propulsion. 4 months later, the contract went to Chrysler, and the Army was forced to adopt the turbine engine. The move was controversial from the beginning. The turbine was lighter, quieter, and had fewer moving parts, but it consumed far more fuel, emitted dangerous exhaust, and required complex air filters to handle battlefield dust. Army leaders feared the engine was too immature for operational deployment. Outside pressures, including Chrysler's worsening financial condition and broader defense politics, meant the safer choice was overridden. By the mid-1970s, Chrysler was struggling. It had lost hundreds of millions in its car division, and its tank business was one of the only profitable parts of the company. For Chrysler, winning the M1 contract was a matter of survival. For General Motors, tank production was minor compared to its automotive empire. The Pentagon knew this imbalance, and Chrysler executives made sure Washington did too. In June 1976, Chrysler chairman John Ricardo met with senior White House economic officials, including William Seidman, a close advisor to President Ford. Ricardo made it clear that Chrysler needed help. While no direct aid was promised, the administration signaled it would support the company where possible. Weeks later, Rumsfeld intervened in the tank competition. Chrysler also kept up pressure on the Pentagon, even threatening a formal protest if General Motors was awarded the contract. The turbine decision fit into this broader rescue effort. For Chrysler, it secured a multi-billion-dollar program and guaranteed years of defense revenue. For the Army, it meant accepting higher costs and unproven technology. Ultimately, Chrysler sold its tank division to General Dynamics in 1982, reaping hundreds of millions just when the company was near collapse. The M1 program became not only a weapons project, but also a lifeline for an automaker the government wanted to keep afloat. Do you enjoy watching our videos? We put a lot of effort into our videos, and our videos are also free. Making them isn't free. If you've gotten value from this channel and want to help keep daily uploads going, buying us a coffee through the link below makes a real difference. Every generous contribution goes straight back into the channel, making improvements to our videos and keeping daily uploads possible. Thank you for the support. Now, back to the video. Now here's what the AGT 1500 actually does, and why its performance characteristics are both its greatest strength and its most significant operational liability. The AGT 1500 is a multi-fuel capable engine. As the knowledge base documents, it can run on JP8 jet fuel, Jet A1, diesel, gasoline, marine diesel, or kerosene. The US Army adopted a single fuel policy, JP8, for both aircraft and ground vehicles to simplify logistics in the field. In theory, a tank and a helicopter operating in the same area can draw from the same fuel supply. The logistical simplicity of one fuel type for all platforms was a genuine operational advantage that the Army valued. The turbine generates 1,500 horsepower, allowing for high speed and acceleration that support offensive armored tactics. The engine is smaller and lighter than a comparable diesel engine, producing similar power, a significant advantage in a vehicle where weight and space are constant engineering constraints. The turbine also starts reliably in extreme cold, a condition that can make diesel engines difficult to start without preheating. But here's where the operational cost becomes clear. As the knowledge base documents, the turbine is extremely fuel hungry, getting roughly 0.5 to 2 miles per gallon. A typical M1 tank battalion requires significantly more fuel tankers and support vehicles, including added 5-ton trucks and 5,000-gallon trailers, to keep up with the high fuel demand. The turbine consumes 83% more fuel than diesel-powered counterparts, increasing the logistical burden. The idle consumption problem is particularly significant. The tank uses high amounts of fuel even when sitting idle, leading to the need for added auxiliary power units. A tank that is stationary, waiting in a defensive position, conducting surveillance, or providing overwatch, is still consuming fuel at a rate that a diesel engine would not approach. In a sustained operation where tanks spend significant time in static positions, the idle consumption of the AGT 1500 creates a logistical burden that has no equivalent in diesel-powered armored forces. The thermal signature problem compounds the operational liability. The engine produces extremely hot exhaust, making it easily detectable by enemy thermal optics. A tank that is thermally visible to enemy surveillance systems at greater ranges than a diesel-powered equivalent is a tank that is easier to target. In an era of increasingly capable thermal imaging systems on both sides of any potential conflict, the AGT 1500's thermal signature is a genuine tactical disadvantage that did not exist as a concern when the engine was selected in 1976. The AR filtration requirement adds another layer of operational complexity. The gas turbine ingests enormous volumes of air, far more than a diesel engine of comparable power output. In desert environments, the air is laden with fine sand and dust particles that are highly abrasive to turbine components. The M1 Abrams requires sophisticated air filtration systems to protect the AGT 1500 from the desert environments where it has most frequently operated. Those filtration systems require maintenance, can be damaged by battle damage or rough handling, and add weight and complexity to the vehicle. Here's what the fuel consumption means in actual operational terms. The M1 Abrams has a fuel capacity of 504 gallons. At the lower end of its fuel consumption range, approximately half a mile per gallon in cross-country operation, that fuel load provides a range of approximately 265 miles before refueling is required. At higher consumption rates in demanding terrain, that range decreases significantly. A standard United States Army armored battalion operates approximately 58 M1 Abrams tanks. At a consumption rate of 10 gallons per mile of cross-country movement, a figure consistent with the knowledge base's documentation of the turbine's fuel consumption characteristics, a battalion movement of 50 miles requires approximately 29,000 gallons of fuel for the tanks alone, before accounting for the fuel requirements of the supporting vehicles, helicopters, and other equipment in the task force. As the knowledge base documents, the turbine consumes 83% more fuel than diesel-powered counterparts. If the same battalion were equipped with diesel-powered tanks of comparable capability, the fuel requirement for that same 50-mile movement would be approximately 15,800 gallons, a reduction of over 13,000 gallons per battalion movement. Across a corps-level operation involving multiple battalions moving simultaneously over extended distances, the cumulative fuel savings of a diesel power plant would represent a logistical advantage of enormous operational significance. The idle consumption problem is quantifiable. The AGT 1500 consumes approximately 10 gallons of fuel per hour at idle when the tank is stationary with the engine running. A tank that idles for 8 hours in a defensive position consumes 80 gallons of fuel without moving an inch. A diesel engine in a comparable tank would consume a fraction of that amount at idle. In operations where tanks spend significant time in static positions, which describes most defensive operations and many urban warfare scenarios, the idle consumption of the AGT 1500 creates a fuel demand that has no tactical return. The diesel alternative to the AGT 1500 was not merely a theoretical possibility. As Slashgear documents, in the late 1990s and the early 2000s, General Dynamics Land Systems tested diesel-powered Abrams prototypes using the MTU MT883 V12 as part of the Euro Power Pack. Trials showed the diesel variant matched the turbine version in mobility and firepower, while offering reduced operating costs. A second tested option, the Continental AVDS 1790 V12 diesel, also promised better fuel economy. These designs were evaluated for export customers, such as Turkey, and for potential US Army upgrades, but were never adopted. More recently, as Slashgear notes, the Abrams X demonstrator has introduced a hybrid diesel-electric system, claiming 50% better fuel efficiency than the AGT 1500. Despite these developments, the US Army has retained the turbine for operational Abrams fleets, prioritizing its acceleration, multi-fuel flexibility, and established maintenance infrastructure. The decision to retain the AGT 1500 despite the availability of diesel alternatives reflects the institutional momentum that large procurement programs develop over decades. The Army has trained generations of mechanics on the AGT 1500. It has built a maintenance and supply infrastructure around the engine. It has developed an operational doctrine around the tank's performance characteristics. Replacing the engine would require not just a new power plant, but a new training program, a new supply chain, and a new set of operational procedures. The sunk cost of the existing infrastructure is a genuine factor in the decision to retain the turbine, separate from any assessment of the engine's operational merits. The Chrysler connection adds a historical footnote that the procurement record makes clear. As Slashgear documents, Chrysler sold its tank division to General Dynamics in 1982, reaping hundreds of millions just when the company was near collapse. The company that needed the M1 contract to survive did not ultimately build the tank it was awarded the contract to produce. General Dynamics has manufactured the M1 Abrams ever since. The political and financial pressures that drove the turbine decision in 1976 benefited a company that no longer exists in the form that lobbied for the contract. You have been surrounded by the engineering trade-offs of the gas turbine versus diesel decision your entire life without recognizing it. The fuel consumption difference between a gas turbine and a diesel engine is the same trade-off as the fuel consumption difference between a sports car and a fuel-efficient sedan. The sports car produces more power, accelerates faster, and delivers a more dramatic performance experience. The sedan travels significantly farther on the same tank of fuel. Both are correct choices for different priorities. The M1 Abrams chose the sports car engine for a vehicle that needs to travel very long distances in the field. The logistical consequences are exactly what you would expect. The idle fuel consumption of the AGT 1500, approximately 10 gallons per hour at idle, is the same problem as leaving a high-performance engine running in a parked vehicle. The engine is doing no useful work. It is consuming fuel at a rate determined by its design, not by the task it is performing. The solution in civilian vehicles, turning the engine off when stationary, is not always available to a tank crew that may need to move immediately. The auxiliary power unit that the knowledge base documents as a solution to the idle consumption problem is the military equivalent of a hybrid vehicle's ability to shut down the combustion engine when stationary and run on battery power. The single fuel policy JP8 for both aircraft and ground vehicles is the same logistical simplification principle as standardizing on a single type of battery across all devices in a household. One battery type means one purchasing decision, one storage location, one supply chain. The Army's JP8 policy means one fuel type for helicopters and tanks operating in the same area. The simplification is real. The constraint it imposes using a fuel optimized for aircraft in a ground vehicle is also real. The thermal signature problem, the AGT 1500's hot exhaust making the tank more visible to thermal optics, is the same physics as the heat signature of any high-temperature exhaust system. The reason thermal imaging cameras can detect vehicles by their exhaust heat is the same reason the M1 Abrams is more visible to enemy thermal systems than a diesel-powered equivalent. The exhaust temperature of the AGT 1500 is higher than that of a diesel engine of comparable power output. Higher exhaust temperature means greater thermal contrast against the background environment. Greater thermal contrast means greater detection range. The physics is identical whether the thermal imaging system is a military targeting system or a civilian building inspection camera. The air filtration requirement for the AGT 1500 in desert environments is the same engineering challenge as the air filtration systems on industrial gas turbines used in power generation. Power plant gas turbines operating in dusty environments require sophisticated inlet filtration systems to protect the turbine blades from abrasive particles. The M1 Abrams and the power plant gas turbine are solving the same problem, protecting a high-precision rotating machine from airborne contamination with the same solution, inlet filtration at different scales, and in different environments. The institutional momentum that keeps the AGT 1500 in service, despite the availability of more fuel, Efficient alternatives is the same force that keeps legacy systems in place across every large organization. The cost of replacing an established system includes not just the hardware cost, but the training cost, the infrastructure cost, and the operational disruption cost of the transition. The Army's reluctance to replace the AGT-1500, and the reluctance of any large organization to replace a deeply embedded legacy system, are driven by the same institutional economics. Now, for the honest part, because it is significant and the knowledge base is clear about it, the AGT-1500 is not simply a bad engine that should never have been chosen. It has genuine operational advantages that the diesel alternative cannot fully replicate. The turbine's power output, 1500 horsepower, gives the M1 Abrams a tactical mobility that has proven decisive in every armored engagement the tank has fought. The rapid acceleration that allows the tank to move between covered positions faster than an enemy can track and engage, it is a direct product of the turbine's power-to-weight characteristics. The multi-fuel capability, the ability to run on diesel, gasoline, kerosene, or jet fuel, provides a logistical flexibility that a diesel engine optimized for one fuel type cannot match. As Slashgear documents, the decision prioritized performance, speed, and acceleration, and the ability to use the same fuel as nearby helicopters for logistical simplicity over fuel efficiency. That prioritization reflected a specific vision of how armored warfare would be conducted: fast, offensive, maneuver-based operations where tactical mobility was the decisive factor and logistics were a secondary concern. That vision was validated in Desert Storm in 1991, where M1 Abrams tanks executed one of the fastest large-scale armored advances in military history, covering hundreds of miles in days and destroying Iraqi armor at ranges and speeds that the Iraqi forces could not match or respond to. The AGT-1500's performance characteristics were central to that operational success. What the Desert Storm experience also revealed was the logistical burden the turbine imposed. The fuel consumption of the M1 Abrams fleet during Desert Storm required a supply chain of extraordinary scale. The fuel tankers, the distribution points, the forward fuel operations, all of it was larger and more complex than it would have been with a diesel-powered fleet. The operation succeeded in part because the United States had the logistical capacity to sustain that fuel demand. Against an adversary capable of disrupting that supply chain, the fuel consumption of the AGT-1500 would be a more significant vulnerability. So here's where you actually land. You came in hearing the sound of a jet engine in a tank and wondering why. What you now understand is that the sound traces back to a July 1976. Decision made not by Army engineers at Aberdeen Proving Ground, who had already chosen a diesel design, but by civilian defense officials responding to political and financial pressures that had nothing to do with what happened in the testing arena. A struggling automaker needed a contract to survive. Pentagon officials believed the turbine represented the future of armored propulsion. The Army's recommendation was overridden. The contract went to Chrysler. The AGT-1500 went into the M1 Abrams. The engine that resulted is genuinely extraordinary. 1,500 horsepower, multi-fuel capable, rapid acceleration, reliable cold weather starting. The performance advantages are real and have been validated in combat. So is the cost. 83% more fuel than diesel counterparts, 0.5 to 2 miles per gallon. Significant idle consumption requires auxiliary power units, a thermal signature that makes the tank more visible to enemy systems, an air filtration requirement that adds complexity and maintenance burden in the desert environments where the tank most frequently operates, a logistics tale that shapes how the Army plans and executes armored operations at every level of command. The M1 Abrams is the most capable main battle tank ever built. The engine that powers it was chosen for reasons that included, but were not limited to, its engineering merits, and the Army has been managing the consequences of that decision in fuel tankers, in logistics planning, in operational constraints for more than 40 years. That sound you hear in the footage, that turbine whine where a diesel rumble should be, is the sound of a political decision made in 1976, still echoing across every armored operation the United States Army conducts today. And if you think the decision to put a jet engine in a tank created unexpected operational consequences, wait until you find out what happens when that same tank takes a direct hit from a modern anti-tank weapon, and the crew survives. The armor system that keeps 4 people alive inside a steel box being struck by a kinetic energy penetrator traveling at nearly a mile per second is not what you expect. One component of that protection system works on a principle so counterintuitive that the engineers who first proposed it were told it was impossible, and it has saved more lives in armored combat than any other single innovation in tank design since World War II.